Hello, my name is Patrick Simmons, and I am an applications engineer supporting position sensing products. Today I will be going over the general grip detection concept, talking a little bit about the theory of operation for the LDC3114, then diving into the demo and its implementation, and then ending with a few resources used in this design process that we have available online. At a high level, this design utilizes our Boost LDC3114 EVM and a 3D printed handle to implement a low-power grip detection that is based on the force of the grip. This allows the solution to be robust against damage, dirt, debris, and it allows it to work well with gloves. In the design, I am comparing the state of multiple sensors so the solution can determine the difference between the handle resting on another surface and a hand wrapped around the grip. If you aren't familiar with how our inductive sensing devices work already, there will be a link to another training video at the end that covers the basic working theory of the device. For the grip detection demo, we are treating it the same as an inductive touch button. In this case, we will have a non-conductive touch surface with a conductive target directly below it. The target will couple with the LDC sensor coil, and any deflection in the target surface will be used to determine the force applied to the touch surface and if a button output should be present. Using the LDC3114, we can take advantage of the included baseline tracking algorithm and digital outputs to ease the microcontroller processing needs. Without baseline tracking, environmental factors like temperature or damage to the button surface can cause the button operation to no longer function. Temperature can cause a slow drift in the sensor's measured data and create a state where the digital output is always triggered. At a high level, the baseline tracking algorithm looks for sudden changes in the sensor data and ignores slow changes over time that could be due to temperature. It can even be used to ignore dents of the target surface by adapting to the permanent change in the metal's normal resting position over time. The baseline algorithm in the LDC3114 also compares the data to a set threshold to create a digital output which can be used as a button press response. Now, diving into the grip demo. We are utilizing a 3D printed grip with 3 sensor coils placed around the handle and 1 sensor coil placed in the trigger. The mechanical stack-up of the sensor coil assembly can be seen here on the bottom of the slide. Directly above the plastic is a sensor coil implemented on a flex PCB. On top of the sensor coil is a layer of compressible foam that acts as a separator between the coil and the metal target. Acting as the metal target, we are using a layer of copper tape to cover the entire sensor area. Finally, for the outer surface, we are wrapping the handle in a rubber grip for the user to grab. In order to cover a large portion of the handle, 3 different sensor sizes were used. 2 larger sensors are placed on the sides of the handle to cover where a palm would interact with the grip, while a thinner coil is used at the back of the handle to cover where the webbing between the index finger and thumb will be placed. Lastly, a small coil is placed inside the trigger to cover the width of a single finger. This implementation does not have any mechanical motion for the trigger and solely relies on the force on the trigger surface. For an example of a contactless mechanical trigger, we also have a Hall effect trigger design that is linked below. Now that we have talked about the demo construction, it's time to see it in action. Here we are looking at the data from the LDC3114 EVM being displayed on the GUI. Without anything touching the handle, the data rests at 0, and the LDC3114 is operating in low power mode with a slower sample rate. If I press on the side of the handle, you can see that the data increases and the device stays in low power mode. Additionally, if I push on the trigger in this mode, then nothing happens. Now, if I wrap my hand around the handle, you can see the data change on multiple sensors, and the LDC3114 shifts from low power mode to normal power mode. Now that the device is in normal power mode, the trigger sensor has been enabled and we can see the data change on that as well. Setting the handle back down, you can see that the data is taking some time to go back to zero. This is because the compressible foam used for this demonstration can be a bit slow to regain its original shape, especially after being held down for an extended period of time. Here is a list of all the resources we have available to assist in this type of design. The LDC calculator spreadsheet was used to help design the sensor coils shown in this video, and we have an instructions video on how to get started with it. And that concludes the demonstration of how to use the LDC3114 for a grip detection application. Thanks for watching.